Realistically, we really want it to be a regular polygon, right? Because regular is just way easier. Because then, if it is a regular polygon, we can draw a circle around it. And that's where we came up with finding a new little segment. And that new little segment was the distance from the center of the circle or polygon to one of the sides. And that little special segment was called the what? The abathon. Okay? And so this led us to then either find each individual triangle or use a special formula, right? And what was the formula for a regular polygon? 1/2 PA. And the most important part of 1/2 PA is that you put the correct capital or lowercase letter in it, right? It's capital P and little a. Capital P meaning what? The perimeter of my shape, and little a is then my abathon. Yeah? By the way, we did really good on the, you guys did really good on the formulas. Formulas on the quiz. Okay? So we'll, remind me, we'll hand that back at the end. Okay? Then it led us to our composite figures, which you went over and looked at on the board. And a composite figure is just basically taking a bunch of weird shapes and sticking them together, right? So it's kind of like a blueprint. And you might have a combination of triangles, rectangles, circles, trapezoids, whatever. And then you have to find each individual part and then add them together. Okay? And that's what we'll have that review worksheet on tomorrow. Okay? Today we're going to talk about similar figures. We've kind of talked about this before. If we're talking about similar figures, what's that mean to you?
They're same shape. Same shape.
Same shape, but
Different size.
different sizes.
What?
So,
How
So-
did you notice?
how did I notice?
Because we're smiling.
Because I knew where I put them. So, similar figures, just like you said. Same shape, but different sizes. Now, because we're saying it's a figure, we could do this in other aspects, I guess you could say. Meaning we could do three-dimensional objects. Everybody understand what we mean by a three-dimensional object? That's like my Kleenex box, right? So we actually got a rectangular prism, right? This is a three-dimensional object. And so if you're talking about a three-dimensional object, then we're more specifically talking about what, probably? The what of the shape? The volume or the surface area. Okay? And that's actually what we'll do all next chapter. Okay, but some of that will get brought into play today. Remember when we're talking about similar, what's the symbol for similar? The little squiggly, right? So if we say triangle ABC is similar to triangle EFG, this right here would be called a what? Similarity statement. And what's this tell us? Even without the figures. It tells us what angles go together, right? So those two angles are in the same spot of my three letters. They should be in the same, or they're corresponding to each other. Meaning they're in the same spot of my figures. And there should be, what's true about angles in similar figures? They're congruent, right? So angle A should be the same thing as angle E. And then so on and so forth, right? But also, it does it with the sides, right? So because BC is together here, BC and FG should be in the same location. So even if one shape's upside down, this can help us show what is similar to each other. And what's true about the sides?
Proportional.
They're proportional, right? So, again, if you need to remind yourself, the angles, or let's put corresponding angles, right? And again, that word just means what again? In the same spot. Corresponding angles are congruent, but corresponding sides are, as Mr. Druckmann said, proportional. And so if they're proportional, each set of sides should end up leading us to the same what?
Area.
The same what if they're proportional?
Oh,
The same fraction, right? So this is going to lead us to, if it's proportional, we're really talking about a ratio. But that ratio, when we're talking about similarity, was actually called a what? SF.
Scale factor.
A scale factor, right? It's okay, buddy.
I always thought of it.
You'll get the next one. So, what was special about a scale factor? Again, it should be a fraction. And when we're talking about a scale factor, what was the most important part of the scale factor? That you always had to do what?
Match up. Reduce.
Yeah, match them up in a sense, okay, and reduce, but yeah. So when we're talking about our scale factor, remember we're going to do the big triangle to the small triangle. And if we start out that way, we got to continue that way through the entire process. Or we could do it the other way. So realistically, every single problem has how many scale factors?
2. Hey, how is that supposed to know that?
Because we've already talked about it.
When?
When you get scale factor.
So, if we have big to small, or we can do what? Small to big, we just have to stay consistent. But it's just a fraction, and what do we do really with that fraction?
Reduce it.
Flip it over, right? So, if my original scale factor from big to small was 3 to 2, then this one would be what? 2 to 3. So every single set of similar objects has 2 scale factors. Okay? Man, that was a great lob for the alley-oop, and you flat missed the dunk.
Yeah,
I missed the light
got
bulb.
five, though.
Because you can't even get to the net.
Yes, I can.
Let alone the lob.
I can easily dunk it. No, you can't. Not easily, but.
Wait a minute, what did you just say?
Drake saw me dunk it in practice. Yeah, he did. Look at his face, he's lying. You were in practice.
With what? A golf ball?
No, basketball. Him and Ryan Augustine both saw it.
Alright.
Just in the layups.
I will
In
talk to
practice.
Ryan because he won't lie. Drake?
Okay. Drake would lie. Look at his face.
Alright, so, are we okay with this? So when we're talking about similar figures, we're talking about the scale factor. Remember way back when, I think it says 7.2 up here, we said that perimeters could be found using these scale factors. Because remember, when we're talking about a perimeter, I think there was an actual test question on this, wasn't there? Yeah, we didn't do it real well on this one.
Oh, yeah.
So remember, if you have a perimeter of one of your shapes, and they don't give you the perimeter of the other, but you could figure out the scale factors of them, you could use that scale factor and set up a proportion with the perimeters, as long as you put this perimeter from the small in the same spot, like Cam was saying, right? So if you did this one right here, where you're using 2/3, then your small perimeter would have to be on top and your big perimeter would be on the bottom. Remember when we said that? Okay? Well, now you can also do the same thing with areas. So this works with areas, and if we actually wanted to go further, we could say it works with volumes. But what's the difference between, if we're talking about the perimeter of a shape and its area? What's the biggest difference?
Outside and inside.
Okay, one's on the outside and one's on the inside, but more importantly, the labels. So you're exactly right, the outside and inside is what we're looking at, but what I was getting towards was more the labels of this. When you did perimeters, that's why you could just set it up with this scale factor, because the scale factor was basically the same thing as the label of your perimeter. But now we're talking about areas and what was true about an area. It's squared, right? So when you're going to try to do this same thing with an area, you can still do this. You can set up the area of, let's use big and small again. The small over the area of the big, and that's fine. So we're going to still set up a proportion, but when you stick in this scale factor, which was 2/3, you have to remember to square that scale factor if you're talking about the areas. And then we haven't gotten there yet, but next chapter we'll talk about volumes and what's the difference between the label of that.
It's cubed.
It's cubed. So you could do the same thing with volumes, but then you just have to make sure that you cube the scale factor. So basically you're doing what we've done before, we're just going to do it with areas now. And that means that you have to square this. And sometimes it does get confusing.
So you square at the end then?
You square it, yeah, kind of at the end, but you're squaring the scale factor compared to the areas. So the area, you're going to find the area just like you would normally find the area. And then you're going to say, but realistically, they're going to only give you one of the two areas. They're going to give you the scale factor in one of these two. So you don't take this number and square it. You only square the scale factor part of it. Okay? And then you would take whatever they gave you and square it.
That's it.
So, here's a question. So, again, would you consider all circles to be similar shapes?
Yes.
Are all circles similar to each other?
Yes.
No.
No.
Yes.
No.
Okay, so those of you that say no,
Could be an oval.
That's not a circle.
Circle.
No, it's not.
how is an oval a circle if you call it an oval?
It's around.
No, it's not.
Different type of circle.
No, it's not. An
No,
oval is
it's
an
an
egg.
No, it's not.
An oval is an egg.
Yeah, you're right, yeah.
Okay, so could you play basketball with an egg?
No.
Because why?
It's still a type of circle.
No, it's not. It's an oval.
What's the difference?
It's an
It's a different shape.
Game's like a square circle. A square circle.
Oh my gosh.
Oh my god.
He doesn't have an oval.
Yeah, because it's in circle. It's the same.
By your logic, I mean the
Same.
squares.
Is that a circle?
Yes.
That's a circle. How about this?
That does look like a circle.
That is also a
Okay,
circle.
so bounce it.
What?
Bounce it.
Is it gonna break?
Bounce it. It's wood. Bounce it. Oh, that really conveniently came back up to you. Oh,
That didn't go anywhere.
but if it was a ball, but again, but a ball in this is two different things because why? Why is his argument even wrong?
They're both round.
Okay, they're round.
Sphere.
What?
Ball's a sphere.
A ball's a sphere. So realistically, his argument isn't even right because when he says oval, an oval is a shape, right?
Yeah.
But an egg would involve ovals, but it's more three-dimensional. Okay? So is a ball a circle?
Yes.
A ball is a circle.
Yeah.
It's a sphere.
A ball is a what?
Sphere.
Sphere.
Sphere is a circle.
A sphere is a circle.
So it's ball is a circle. It's like
Why do you consider a ball a sphere?
What?
Why do you consider a ball a sphere?
Because it's a circle.
A ball is a circle.
It's like you're saying you're
Okay.
Imagine.
Imagine this. If I gave you a basketball
Yes.
and Cam had a samurai sword, okay, and he hit that he hit that ball perfect right down the middle, okay, and so you each had a half of a basketball. What would you be looking at? A what? It's a semi. It's only a half a circle right there. If I cut a basketball in dead half, you're looking at a semicircle.
No, you're looking at a circle.
Oh, that's a circle.
Semicircle is a circle.
A semicircle is not a circle. It's a half of a circle, so it's not. No.
It's half.
This video is gonna be great.
Wait, can we keep talking?
Yes.
Keep arguing, get real.
Okay, so let's go back to your ball.
Yeah.
You're saying every basketball, volleyball, softball, baseball are circles.
Yes.
Okay, so how many circles?
I agree. One.
Just one circle.
10,000.
3D circle.
How many?
10,000.
Why do you say that?
Just because it has a block.
Okay. So go back to my samurai sword thing. If I took a basketball and I cut that sucker right down the middle, everybody opens it up. We're not talking about him. What do you see?
A circle.
You see a circle. And if you took the same samurai sword and just started slicing it and slicing it and slicing it, how many circles do you have?
A lot.
A lot.
Could be as many as we possibly could slice, as thin as we could go, right? But they're all what? They're all a circle, right? Okay? Is that the same thing as an egg shape?
No.
Yes. You could do the exact same thing to it.
Yes, you could do the exact same thing, but that shape that you're looking at would not be a circle.
They wouldn't all be
It'd
circles.
be just a different type of.
Because what is the true definition of a circle? The true definition of a circle is that the center of the circle to the outside are all the same distance. So they're all radii. Would that be true in an egg? No. Because when you got to the long end, this radius would be way longer than this one over here. Would you agree with that? So are they circles?
Kind of. But
No,
they're
they're
different
not.
types.
Gabe,
You're almost there. You went from yes to kind of.
Yeah. Okay, so here's the question. Way back to the beginning. Are all circles similar?
yes.
Yes.
Yes. Because an oval is not a circle. Okay, so here's the question. Are all rectangles similar?
No.
Yes.
Can we hear this?
No. They have the same shape. Could be different
Yes.
sizes.
What?
It could be different size.
That's what similar is. Same
That's what
shape,
similar
different
is.
size.
Rectangles can be square shaped different sides.
What?
A rectangle can be a square, so the size
Facts.
is different sides.
So are all squares similar?
Yes.
Yes.
But are all rectangles?
No.
Are all triangles similar?
No.
Are all equilateral triangles similar?
Yes.
Are all isosceles triangles similar?
No.
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 What's true about an isosceles triangle? Two sides. So just because I have two sides that are the same, here and here, are they similar shapes? Because what if I have this steeple, and then I come over here and I have this steeple? Are they the same shape?
No.
Well, they're the same shape, technically, but they're not the exact same shape. You see what I'm saying? Okay, so circles?
Sure.
Yes. Rectangles?
No.
Squares?
Yes.
Triangles?
No.
Isosceles triangles?
No.
Equilateral triangles?
Yes.
Are all right triangles?
No.
No, right? Because the easy ones there are special right triangles, right? 30, 60, 90, and 45, 45, 90. Those are definitely two different kinds of triangles. Okay? Alright, so let's look at a couple examples.
So what's the
What section are we in? Level 5.
What's a basketball rim shape? What? What's the shape of the basketball rim?
Circle.
Because
It can be
why?
triangle because those you can shoot ball through.
Well, you can't you shoot an egg.
But if I throw that egg, I can make it bigger.
Don't make
You
it
can throw a football at a basketball hoop and then go in.
Exactly.
Damn. Alright, here we go. In ABCD, if, sorry, it says if, not in. If ABCD is what? Similar to PQRS. Ladies and gentlemen, when they start out right there, they're basically saying, yes, they are similar to each other. Okay? That's the most important thing. Again, do not forget to write or read the directions. So if ABCD is similar to PQRS, and the area of ABCD is 48 square inches, can I find the area of PQRS?
Yes.
Okay, so what's the first thing that I gotta figure out here?
Your skill
Ratio.
factor.
I gotta find my scale factor or my ratio, right? So, the second most important thing is, you gotta decide how you're gonna do your ratio. How are you gonna do it?
Small one on top.
Small to big. So, do we wanna do 6 to 9 or do you wanna reduce?
Reduce.
So we're gonna say 2/3, right? So again, you could use 6 to 9, but it's gonna just be bigger. Your numbers are gonna be bigger. If we take your calculator away, we know how some of you freak out about calculators. So, now when I set up this fraction, I lost my dot. Where?
Bottom left. And square, right? Where'd it go?
Equals. So, if we do 2 to 3, what do we have to do with my areas?
48 on top.
48 here. Everybody good with that? And X down here. Can I use this proportion?
No, you have to square your scale factor.
So I got to come back to my scale factor because we're using areas, and I have to square that first.
Why would you form it?
Can you just reduce 48 instead of square the whole thing?
Just reduce 48 instead of squaring the whole thing.
Because then you're taking the square root of 48. But that's still working though.
But I'm not taking the square root of the 48.
Okay.
Okay.
Why can't you put 48 down here?
Because we did.
Because
you know that
we did the
so we
small
did
one.
6 to 9, right here. 6 to 9. 6 was in the same spot as, or is ABCD, and they gave us the
So
48.
you're not supposed to go across. You're supposed to-
They have to be across from each other. Okay, so 2/3 squared is what?
4 nines.
So all you have to do is take the top number and the bottom number and square it. So we would have made 4/9 is equal to, and then we have our other fraction, and that's all you have to do. Now you just do the math. So somebody that's got their calculator out, do 48 times 9 divided by 4. So now we're just right back to our true proportion. And what should X represent?
108.
The area of the big rectangle, right? So what do we get?
108.
108. So my answer, it says find the area of PQRS. It's 108 what?
Inches squared.
Don't forget the label, and it's got to be squared because we're still talking about an area.
We're doing volume.
Oh my gosh, I can't control him.
No.
Are we? No. Okay.
No.
Yes, we are. Next chapter.
Yeah, so next chapter.
I thought he said this chapter.
Guys, you're going to this year.
Oh, yeah.
The area of triangle ABC is 98 square inches. The area of RTS is 50 square inches. If the triangle ABC is similar to RTS, find the scale factor from ABC to RTS. This is really important. Notice the last sentence where it says from to. That's how they want you to set up your fraction. So when it says from ABC, that has to be where? On the top. To RTS. Now here's the other thing that's a little bit more complicated with this one. What am I going to do to set up my proportion?
14 over squares equals 98 over 50.
Oh, it's gonna be squared.
Okay. Say it one more time.
14 over x.
14
Oh, squared.
So 196.
over x
Square
is equal to
that. 98 over 50.
98 over 50. Everybody cool with that?
Yeah.
Okay, now what did we say we had to do over here though?
Square.
Okay, so we want to come back over here and square this. So when you do this, what's 14 squared?
196.
So we're going to say 196 is equal or over x squared, and then we keep our fraction. Is everybody good and see why we did that? Why are we doing this again? Because we said if we're dealing with an area, you have to take that scale factor and square it. So even though that we don't know the area or the scale factor, we have to take the portions of the scale factor that we know and square it. Okay, so again, basically we're doing the exact same thing, but after we divide, then our very last step is what?
Square root.
Taking the square root of it. So you should take 196 times 50 divide it by 98, and then take that answer and take the square root of it. And then what is my label for this one?
Inches.
Just inches, right? Because we're finding a portion of the scale factor, and that is just the actual label that they give us. Make sense? So what'd you find out?
19.6.
19.6.
I got 10.
I got 10, bro.
I got 10 too.
If we're supposed to do 50 times 196, get 9,800. Divide by 98, get 100. Take the square root.
Ah, there it is.
There it is. So we all got 10 now?
Yeah.
Okay. They got 7/5.
Maybe
Hold on.
I was right.
196.
I think it's 705.
Oh, there's your 10.
Oh.
Yeah.
Why did you
They
say
said
705?
really cool.
Oh, they reduced the
Oh,
fraction.
yeah, there it is. So we just did that from the beginning, right? Okay. So you see the difference between the two kinds though?
Wait, so could we reduce it if we just didn't do the square root?
Yes. Well, no, you got to square root it no matter what.
Oh, there they did.
Yeah.
They square rooted this, the right side, all the areas.
Oh, yeah, and then you got to square root some.
Some.
Yes. No, that one's confusing. All right. So questions here. Perfect. So, avoid or don't look at the top part because we're not ready for that, for the quiz. The quiz again will be when? Thursday. So again, if you want to do some homework problems, we will do this section right away tomorrow as your startup. Or bell ring or whatever. Okay?
Can I take that quiz?
So we're
that I
doing-
missed?